Now, in this video, I want to discuss differentiability of functions with two or more independent variables. So the question is a function given by multiple variables x of 1, x of 2, up to x sub n, differentiable at a point? So remember, when we were working with functions in one variable, we found out that if f prime of a is equal to the limit as delta x goes to 0 of f of a plus delta x minus f of a divided by delta x exists, then we knew that the function was differentiable at a. This would give us a smooth curve at the point a and f of a that also had a unique tangent line at that point with a slope of f prime of a. When we are working with functions that have more variables, we need to have a well-behaved surface that is smooth and unbroken at our point, and we want something that's going to be similar to a unique tangent line to exist at that point as well, in order for our function to be differentiable at a point on the region we're interested in. In order for us to have differentiability at a point, the difference between the slope of a secant line that passes through the point A and f of a and the slope of a tangent line at the point A will need to be very small. In fact, we want it to approach 0. So if I define epsilon, which is equal to f of a plus delta x minus f of a over delta x minus f prime of a, this is just the slope of the secant line minus the slope of the tangent line, and I want this to be very small. And this is where epsilon will be a function of delta x. If I multiply through by delta x on both sides, I get epsilon times delta x is equal to f of a plus delta x minus f of a minus f prime of a times delta x. I'm going to rearrange this just a little bit. I get f of a plus delta x minus f of a is equal to f prime of a times delta x plus epsilon times delta x. The left-hand side, f of a plus delta x minus f of a, is just delta y. So delta y will be equal to f prime a times delta x plus epsilon delta x, where the limit as delta x goes to 0 of epsilon is 0. Now the function z is equal to f of xy will be differentiable at the point AB as long as fx of AB and fy of AB exist, and the change, also called the increment, which is given by delta z, is equal to f of a plus delta x b plus delta y minus f of AB, can be written as the change in z is equal to fx of AB times delta x plus fy of AB times delta y plus epsilon 1 times delta x plus epsilon 2 times delta y, where for fixed a and b, and epsilon 1 and epsilon 2 are functions that depend only on delta x and delta y respectively, with epsilon 1 and epsilon 2 going to 0 as delta x and delta y go to 0 respectively. The function f will be differentiable in a region R if it is differentiable at all points in the region R. So there are some conditions for differentiability that I want to talk about. If a function f has partial derivatives fx and fy that are defined on a region that contain the point AB, where fx and fy are continuous at AB, then f will be differentiable at the point AB. And I have to remember that differentiability implies continuity. If a function is differentiable at AB, it will be continuous at AB. So let's work an example. I want to show that the function given by f of xy is equal to x squared plus 3y is differentiable at every point in the xy plane. So my change in z will be given by f of x plus delta x, y plus delta y, minus f of xy. This has to be equal to fx of xy delta x plus fy of xy delta y plus epsilon 1 delta x plus epsilon 2 delta y in order for it to be differentiable at every point. I'm going to plug in x plus delta x and y plus delta y into my function and then subtract f of xy. So that what I get is x plus delta x quantity squared plus 3 times y plus delta y minus x squared minus 3y. I'm going to expand the squared term, and I get x squared plus 2x delta x squared plus 3 times y plus delta y minus x squared plus 3y. I'm going to simplify and combine some like terms. I get 2x delta x plus delta x squared plus 3 delta y. Notice that 2x is fx and 3 is fy. I'm going to rewrite this with some parentheses. I get 2x delta x plus 3 delta y plus delta x times delta x plus 0 times delta y. I have to put that 0 in there because I want to be sure that I have the e2 delta y term accounted for. Now let's look at what this means. Comparing this to the expression on the right-hand side, I see that I have 2x, which is fx of xy, times delta x, plus 3 times delta y. 3 is fy of xy, plus delta x times delta x, where delta x is epsilon 1, plus 0 times delta y, where 0 is epsilon 2. You'll notice that epsilon 1 is delta x and epsilon 2 is 0 here, and that epsilon 1 and epsilon 2 do in fact approach 0 as delta x and delta y approach 0. This means that f is differentiable at all points in the xy plane. I want to work another example. I want to show that while both fx of 0, 0 and fy of 0, 0 exist, the function f is not differentiable at 0, 0 when f is given by f of xy is equal to the piecewise defined function, where negative 2xy over x squared plus y squared is the function when xy is not 0, and where 0 is the function value when xy is 0. All I have to do is show that f is not continuous at 0, 0. The easiest way to do this is by looking at the values of f along two different paths that are approaching the point 0, 0. I'm going to pick a path along y is equal to x. The limit as xy goes to 0, 0 is given by the limit as xy goes to 0, 0 of negative 2x squared over 2x squared, which is equal to negative 1. Now I'm going to try looking at the path along the line y is equal to negative x. The limit as xy goes to 0, 0 of my function f of xy will be given by the limit as xy goes to 0, 0 of 2x squared over 2x squared. This is equal to 1. Since the two limit values are different along different paths, the limit does not exist, and we conclude that the function is not differentiable at the point 0, 0. So now you get to try it. Pause the video and using the function defined by f of x is equal to the piecewise defined function given by negative 2xy squared over the quantity x squared plus y to the fourth when xy is not 0, and 0 if xy is 0, determine the following. When you're ready, restart the video to check your understanding. What you want to determine is A, if f is continuous at 0, 0, B, if f is differentiable at 0, 0, and C, if fx and fy exist and are continuous at 0, 0. For the first part, I want to determine if the function f is continuous at 0, 0. I'm going to choose two different paths and see if the limit values are the same. I'm going to first choose y is equal to 0. The limit as xy approaches 0, 0 of f of xy becomes the limit as xy approaches 0, 0 of 0 over x squared. This limit is 0. I'm going to now pick the path along x is equal to y squared. The limit as xy approaches 0, 0 of my function is now given by the limit as xy approaches 0, 0 of negative 2y to the fourth over y to the fourth plus y to the fourth. This simplifies to the limit as xy approaches 0, 0 of negative 2y to the fourth over 2y to the fourth, and this limit value is negative 1. Because the limit values are not the same for these two different paths, the limit does not exist, so that my function is not continuous at 0, 0. Now I want to determine if my function is differentiable at 0, 0, keeping in mind that differentiability implies continuity. Since f is not continuous at 0, 0, it is also not differentiable at 0, 0. Now I want to determine if fx and fy exist and if they are continuous at 0, 0. Because I have a piecewise defined function that explicitly defines my function f of xy to be equal to a function value of 0 when xy is equal to 0, both fx and fy will identically be equal to 0 at that point as well. This means that both derivatives exist at the point 0, 0. Now I'm going to find fx of my function using the quotient rule. I get fx is equal to the quantity x squared plus y to the fourth times negative 2y squared minus negative 2xy squared times 2x, all over the quantity x squared plus y to the fourth squared. This simplifies to 2y squared times the quantity x squared minus y to the fourth over the quantity x squared plus y to the fourth squared. My fy, using the quotient rule, is given by the quantity x squared plus y to the fourth times negative 4xy minus negative 2xy squared times 4y cubed, all over the quantity x squared plus y to the fourth squared. This simplifies to 4xy times the quantity y to the fourth minus x squared over the quantity x squared plus y to the fourth squared. Now I'm going to let x equal 2y squared. Substituting 2y squared for x, fx becomes 2y squared times the quantity 4y to the fourth minus y to the fourth over the quantity 4y to the fourth plus y to the fourth squared. This reduces to 6 over 25y squared. Fy with 2y squared substituted for x gives me 4y cubed times the quantity y to the fourth minus 4y to the fourth, all over 4y to the fourth plus y to the fourth squared. This reduces to negative 24 over 25y. In both cases, I have a y that appears in the denominator. As y approaches 0, my rational expression is going to get larger and larger. This means that as y approaches 0, neither fx nor fy will converge to a finite value, so that neither function will be continuous at 0, 0. This is how differentiability applies to partial derivatives. Be sure and let me know if you have any questions.